All right, let's keep trucking. Let's see. So last time, we talked about a bunch of different things. We talked about TCP/IP. The main problem that TCP/IP is solving is solving the problem of making sure your data arrives uncorrupted and it handles all the resending and things like that. Kind of fixes, when we connect it back to a historical thing, it fixes the need for that handshaking that our dial-up modems used to have to go through, where they had to figure out what's the fastest speed that we can talk to each other without screwing up. Because now, not that you want data communication to have problems, but now if it does have problems, they automatically recover from them as long as they're using TCP over IP. Now, having said that, there's and the TCP/IP over IP, TCP over IP on an Ethernet-based network has a higher chance of there being collisions, because it's Ethernet is what's called a bus-based network. Everybody's on the road at the same time. I think I used the analogy kind of like I noticed traffic in like Hyderabad. You know, everybody's everywhere all at once, and they're all going different directions and stuff like that. So there's a chance that there, you know, could be two packets that hit each other. But now we have two different ways of using this protocol. One is TCP, where we want to guarantee the data does eventually arrive. And the other one is UDP, which is typically used for like video streaming, where, you know, we would really prefer that a high majority of the data does arrive. But if we lose a frame here and there because of data corruption, we're just going to let that go. We don't want it to resend because we don't want our video to pause over one frame. So similarly, UDP is often used in like video game communication. We talked, I think probably week one, about the amount of data that kind of moves between your computer and the server and other computers when you're playing a video game. And it's really not that much data, because it's usually text-based stuff that's being sent. All those graphics and things like that are being rendered on your local computer. They're not leaving your computer anywhere. Anyway. Well, if you think about a game like Call of Duty or something like that, where the whole lot of stuff is happening very, very quickly, and it's effectively a real-time experience, well, then the situation is that, you know, you want to send those things over UDP, datagram packets, so that they just keep sending over and over and over again the most up-to-date information. And if a packet gets dropped, you know, you don't want that to happen too often, again, just like video streaming, but you're not going to resend it because something, you know, that happened 2 seconds ago is no longer useful if you, you know, if you resend it. So these are, one's not necessarily better or worse than the other. These are different ways of sending data across a Ethernet, well, different ways of sending data off across any network. Typically, we're using an Ethernet-based network, but we get to choose whether we want packets to resend in the case of an error, or we don't want them to resend. Kind of a interesting use case that we have in the end. All right, we talked about IP addresses, and we're going to talk about IPv4 versus IPv8 today, or v6 today rather. I think we actually started talking about it last time. So an IP address is a unique, think of it like a phone number, a unique value that we can use to uniquely identify a computer on a network. And that's kind of the important thing when we talk about IP addresses, is it depends on what network we're viewing things through. And what I mean by that is, if we're thinking about the entire internet, so a computer lives on the internet, and we want it to be uniquely identifiable on the internet, then it would have something called a routable IP address. So that's kind of what we're talking about here. So a routable IP address is an IP address that is unique across the entire internet. as opposed to a non-routable IP address, which is typically, I think I have a picture here. A non-routable IP address might look like this, where the internet lives out here. And this home router, which is also a computer, so even though this is a piece of network equipment, it's going to get its own IP address. So all these are effectively computers. Switches aren't, but this router will get an IP address. So this IP address, by my example here, presumably has a unique IP address, a routable IP address across the entire internet. So this guy has a unique IP address. All of these machines inside of this network, they have a non-routable IP address. They are unique within this network. All right, they're unique within this network, but not necessarily unique across the internet. So if I go, actually, I'm not sure if I get a routable or a non-routable here. Let's see. Yeah, I get a non-routable. All right, so I just looked at my IP address. I'm on the CUWCS Wi-Fi network here. And my IP address is a 192.168.221.12. Now, for those of you who have home-based networks or in an apartment building that has Wi-Fi or something like that, if you looked at your IP address, there's a very, very, very high chance that your IP address starts with a 192.168 or a 10 dot something. So those are the kind of two common non-routable IP addresses. So whenever you see a 192, that's going to be a non-routable IP address. And whenever you see a 10 dot, it's going to be a non-routable IP address. And those are used for presumably smaller networks, smaller meaning not the entire internet. That could still be a pretty big network. Because again, if you're thinking about, I think I had it on this slide, right? With an IP address, each block, so each thing between the dots is 8 bits. So we can have 4.3 billion unique computers in a single IP address. Okay, so now if we're dealing with the 10 dot and the 10 has to be stuck, and we're dealing with the 192 dot and that needs to be stuck, then it's really 8 to the third power. Actually, that's not right. Yeah, it is. Oh, because it's this. It's 256 times 256 times 256. It's not 8, it's that. So that means we have 16,772,216 theoretical non-routable IP addresses within a network. Since we're sticking with the 192 and the 10, though we don't get options on those stay. So that means technically we can have 16.7 million computers inside of our local area network here with non-routable IP addresses, with one real routable IP address talking to the internet. And the job of this router, as its name implies, is to route requests to and from these computers. So if this computer here wants to go to google.com, it makes the request to the local network. That local network then makes the request to the internet on behalf of that computer. We'll talk about what that looks like today. It receives the response here and then routes the answer back to that computer. All right, so it's making these phone calls, if you will, internet requests on behalf of these inside computers, where each of these inner computers have a unique IP address among this network. But in most cases, these computers would have non-routable IP addresses. That is, if this guy is 192.1, let's say this is my computer here, 192.168.221.12. If you tried to connect to my computer from the internet, from wherever you guys are sitting right now, you wouldn't be able to, because there's a decent chance there's an IP address with the same IP on your local network. My IP is not unique across all the internet. Lots and lots and lots of different computers very likely have this exact same IP address right now. So you can't get to it that way. Only if I had a real routable IP address could you possibly talk to my computer. Now, another job of these routers, I think we mentioned last time, is they can also act as a firewall. So even if, let's say here on campus, they gave my computer a routable IP address. So let's say it was unique on the entire internet. That doesn't mean that my router here won't still make requests on my behalf, because those are two separate kind of services, if you will. But if let's say I made an arrangement with IT and my computer needed to have, I was running a server off my computer that needed to be accessible across the internet or something. Most IT places probably would not do that because there's some security concerns with that. But effectively, let's just assume that's the case. So I have a real IP address that's routable across the internet. It would still be unique on this network, although there would be some issues with something called a subnet mask and stuff like that, which we were not really going to get into those details. But let's just assume it's not a problem. Then you could try to reach my computer directly. But a couple different things are going on here. To get to my computer, you still have to get through this router. And if that router has incoming connections blocked, if it's acting as a firewall, in order for me to allow connections to get to my server, they'd have to open up a port on the router. They'd have to do something called port forwarding. And probably actually in that particular case, you would externally hit the IP address of the router, and then it would, so maybe if I'm running a web server, you would go to the router on port 80, which would then forward that request to my computer on port 80, something like that. So these things are possible, but you're kind of playing this game of, do I have a real IP address or do I have a non-routable IP address that just makes me unique on my network? And then do I use my router to make requests on my behalf? Most setups are like that, because most of us, when we're on the internet, we are a consumer of the internet, not a data provider on the internet. All right. Now, having said that, let me duplicate this slide here. Last time we did talk about something like BitTorrent. And the idea is that, if we are multiple networks that presumably are in different places. So, maybe this is New York City, this is Moscow, this is Hyderabad, Mumbai, you pick your favorite place in India. So these local area networks are all over the world, and we might be using something like BitTorrent to communicate between them. All right. The idea here is that these computers, remember we talked about BitTorrent, and each computer is kind of, as they're sharing a large file, as a computer gets bits from that file, it then shares those bits with other computers. Well, a computer from this network cannot talk directly to a computer in this network. They just can't do that. So they have to have a way of reaching out, bypassing the connection. And we have a couple different ways we can handle this. So some networks, what they'll do is all of these guys will connect to a server. So we will get a communication channel established. So now all of these three networks, even though they can't talk directly to each other, they can potentially reach each other by them opening up a connection to a server up here. So maybe this computer over here opens a connection to this server. This computer over here opens a connection to this server. and then this server connects those two connections together. Okay, just acts as a middleman between them. Okay, so you can almost think of this guy as being the quarterback, because these firewalls, these routers that live here, they are blocking incoming connections. Now, actually, having said that, nothing keeps an IT person from blocking internal connections from going external. So for instance, they could just say, look, we're not going to make any requests for you. You know, if they really wanted to be a jerk, they can say, we're not going to make any web requests for you. You know, chances are the most used protocol on the internet is HTTP. I don't have data that proves that, but I feel fairly confident in saying that's probably the most used. Although, you know what, there's a lot of video streaming these days, but I bet you web browsing is still number one in terms of most used protocol. So if somebody wanted to be a jerk, they could say, okay, we're not going to allow you to do any communication over port 80. So now even this internal computer, if they try to go to google.com, which we saw last time is actually going to try to go to google.com on port 80. If this router is saying, yeah, we're going to block any requests on port 80, well, you're not, the internet's not going to work for you is what's going to come down. There might be other reasons why the internet doesn't work, and we'll talk about that probably actually today. I think I have a slide for it already that almost as a consumer, how do you diagnose when your internet is down at your house? Okay, and what are the reasons that it's down? All right, but in any case, if you are working with a non-routable IP address and this computer is going to send and receive data with this computer, they would both need to open up a socket connection to a server outside of their network, which can then connect those two together in various ways. It could directly link them together. It can act as the intermediary where you send data to the server then sends the data back. That would kind of, for BitTorrent specifically, that would defeat the purpose, because remember, one of the problems that BitTorrent is trying to solve is to maximize your internet connection, maximize your download. And what that ultimately means is if you were making all your requests through a central server, all the data is flowing through that server. So that server's upload and download are being used for every internal connection, presumably running out of bandwidth there as well. But if this guy's only job is to take two incoming phone calls and connect them together, then it can kind of work. All right, you end up becoming part of the mesh, the mesh network of BitTorrent, with all these computers talking directly to each other, but they both had to reach out beyond their network. They had to open up a communication channel past their router in order to make that connection. All right, so that's how something like BitTorrent might work, where multiple computers have non-routable IP addresses. So you certainly can't reach that computer directly, but if that computer reaches out a communication channel, you can then link another communication channel to that communication channel and just follow the pipe back to the computer. You no longer need to have its IP address. Now it's reached out and say, I want to be part of this conversation. All right. And we see that all the time. You know, forget about BitTorrent. You can think about, you know, we can very easily replace this with like, you know, some sort of chat, chat program. You know, so pick your favorite, internet chat. We use Slack, here on campus, but, all of these chat things are going to have you go to a central server, and it doesn't matter where you live on the network. As long as you've connected to it, you've established a communication channel. All right. Now, I know we started talking about this last time. Did I get to it? No, I didn't get to it there. But our modern day networks are almost all IPv4. So that is 8 bits, 8 bits, 8 bits, 8 bits. IPv6 expands the number of unique IP addresses because the idea is we're running out of IP addresses. There are more than 4.3 billion computers either actively on the internet or, and this is maybe the bigger problem, it's how the IP addresses were handed out in the earlier days, is let's take a place like Concordia. They would hand out a block of IP addresses to Concordia. So Concordia would make a request and say, okay, well, you know, we have 1,000 computers on campus that need to have real IP addresses. They would then give, you know, whatever the smallest collection, it would be a power of 2, number of IP addresses to Concordia, whether we were going to use those IP addresses or not. Those are now flagged as used, you know, because they've been handed out to us. They can't be handed to anybody else at that point. So even if there aren't 4.3 billion unique devices on the internet, there might be 4.3 unique IP addresses that have been handed out. I don't think we're quite at that number yet, but we're getting close enough to that number that we need to start considering, well, we need a bigger way of handling IP addresses. We need more IP addresses. So we can't do 8-bit by 8-bit by 8-bit by 8-bit. We need to expand that somehow. So the next one is this IPv6. Talked about routers, talked about how a router can be used as a firewall to protect the inside computers from external entities, but we can poke holes in a router to allow ports to be forwarded. We talked about what ports are. We talked about some common ports like web is HTTP, FTP is port 21, Telnet's port 23. And then as a user, you can write software and utilize any port that your computer is currently not listening to. As long as the port's available, you can think of these ports as kind of like being, you know, extensions on a telephone network. When somebody connects to your IP address, you dial a phone number, and then it says, you know, if you know your party's extension, dial it now, something like that. Well, at a computer has an IP address. Once you've reached that computer, you can divert to one of the ports, like a phone extension, and some of them are already being taken. But if you're writing software and you say, okay, I want my software to listen on port 7,000, as long as no other computer or no other software in your computer has claimed port 7,000, you can start using that port. Typically, ports less than 1,024 are reserved for the operating system. So ports, if you're writing a user program, you would have to use ports above 1,024, but not the end of the world. All right, so kind of, we've already explained this at the high level. How do we solve a problem? So we're going to say this guy solves the problem of a non-routable, let's see, I have a computer with a non-routable IP address wanting to talk to the internet. Since that computer is not uniquely identifiable on the internet, we need a mechanism to translate its requests as if they came from a computer that is uniquely identifiable, and then have that computer map the response back to the non-routable IP computer. All right, and we've already talked about that at the high level. We said, you know, if this guy here has a real IP address, has a routable IP address on the internet, and this desktop here does not, it has a non-routable IP address that's only unique within this local area network. Well, then when this guy makes a request, he's making the request through the home router. The router is then making the request on that guy's behalf. That's network address translation. So this guy is going to remember that, okay, this dude wants google.com. So I'm going to ask for google.com. And when I get my response, I'm going to make sure I pass the answer back to this guy. That's effectively how a NAT works. And NATs are used all over the place because really a NAT is the tool by which we get all of these non-routable IP addresses. So when this home router is acting as a NAT, it's agreeing to say, I will make requests on your behalf and hand out the responses as they come in. I'm also saying I'm likely going to be creating a local network filled up with things with non-routable IP addresses so that we're only utilizing one routable IP address to talk to the internet. And more importantly, we only have one point of failure. So from the rest of the internet, we only have one computer that can be directly released. So we only need to secure this one computer in order to protect our inside network. Because from the internet, you can't reach this guy directly. Your only way is through this guy. All right, so that's what a NAT is, if you ever see that. So we might even go on and say, this is the typical mechanism with which we create local area networks with non-routable IPs. So now in this same equation, since we're talking about this guy right here operating as a NAT, where he has a real IP address and all these inside computers have non-routable IP addresses, but they still have to be unique IP addresses on this network. The old way of doing this is we would have had to go around and we would have had to manually enter in IP addresses. We would have had to say, okay, well, this guy is 192.168.1.1. This guy is 192.168.1.2, 192.168.1.3, so on and so forth. We would have to go through and hand each one a unique IP address and make sure that we didn't give this guy the same IP address as this guy, because then they would have a conflict, because IP addresses are meant to be unique on a network. Now that could be a little tedious, especially if you're adding computers to a network and you have to go in and hard code in these manual IP addresses. So we have this thing called DHCP. So that router, this guy right here, might be running a DHCP server. Okay, so now in this case, server is a piece of software that is serving some purpose, some service. All right, so this router is acting like a hardware server for this network, but on this hardware server, there's a bunch of different computer programs that are running that are providing services for this network. We talked about the NAT server, so its network address translation is occurring. Also, more than likely, DHCP is occurring. So with DHCP, dynamically hands out IP addresses within a range to the connected network computers. This range might be routable IP addresses in the event, like I used the example earlier, where maybe Concordia was handed out a whole bunch of IP addresses. And so maybe if all the computers inside the network happen to be routable, which they're not, we saw my IP address is, but if they were, then that DHCP server would hand out from that collection of IPs that have been given to Concordia, it would hand out a unique one to each computer that asked for it. But more commonly, when this computer asks this guy for an IP address, he's going to hand out a non-routable IP address, an IP address that makes sure that this guy is unique on this internal network. All right, but that way we don't have to manually handle IP addresses. Okay, now one interesting thing with this is, and you maybe have seen this before, actually I'm going to put it on this slide first. There is typically a lease time where the computer with the same what's called MAC address, that's a unique hardware identifier on a piece of network hardware. This guy gets the same IP address during that lease time. So that means that, for instance, my computer right here, when I come and I connect to the network tomorrow morning, let's say, presuming the lease time is usually fairly long, I will very likely get the same IP address again. So there's a high probability that I will continue getting this same IP address over and over and over again. Okay. Oh, and notice here, like I mentioned, MAC address. This is the MAC address for my particular network interface card in my computer. So this value right here, these are hexadecimal values. So this is 4 bits. Hexadecimal is 0 through 9, A through F. So the entire hextet thing can be represented as 4 bits. So this is 8 bits, 8 bits, 8 bits, 8 bits, 8 bits, 8 bits. So that's 256, 1, 2, 3, 4, 5, 6, 256 to the 6th power. That's the number of unique hardware devices that can exist. So that's thousands, millions, billions, trillions, 281,474,976,710,656. So that's the number of pieces of network hardware that have to be created before we run out of unique MAC addresses. That's a lot. Okay. So the purpose of that is that then a computer typically would have a reliable IP address, but this sometimes can actually cause a problem. And that problem is let's just say within this network, let's say I was running a web server. Now, even though computers externally from the internet might not be able to reach this guy still has a unique IP address within this inside network. So if I'm running a web server, even if it's on 192.168.14.21, whatever my address was, this guy could connect to this computer on port 80 and view that website. So let's just say that, this guy is somebody who might need to access my website for whatever reason. I might give him my IP address and say, oh yeah, whenever you need it, just hit 192.168, yada, 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 and on port 80, and you'll be able to see my site. What I'm saying here is there is no promise that this guy's IP address will remain the same. It will commonly remain the same for a while, maybe even for a long, long time. That goes along with the DHCP's lease time. All right, but usually the lease time is a relatively long period of time, but there is not a promise that that's the case. So without notification, next time this guy gets onto the router and the router uses DHCP to hand out an IP address, it might actually give this guy a different IP address, where now this computer is trying to connect to an IP address that either hasn't been handed out to a computer, or maybe it was actually handed out to a different computer this time. So you can't necessarily rely on that with DHCP. It's somewhat of a moving target. But now something that's interesting with this idea of DHCP, we're going to call this getting banned from an internet service. All right, so let's say you're a video game player and you decided to break the rules. You know, you might have used a piece of software like a bot or something like that to try to automate the game, or you're doing something else to not play fair, let's say. The video game people might say, okay, well, this person's bad for our community, so we're going to go ahead and ban them. We're gonna ban their account. So we might say, how is a user banned from an internet service? Well, maybe the most obvious starting point is ban the user's account. But if you ban the user's account, then technically that user can come back in and just create a new account, right? And even if they had done some stuff to build up maybe their character or something like that, they can just do that again, and then they're back to cheating again, and hopefully they don't get caught the next time. So what's the next thing they can do? Well, they can maybe ban the user's credit card. So if it happens to be a game where you're paying like a monthly subscription or something like that, and replace game with web streaming service or whatever, you know, it's just something on the internet, some service that you're using and that you are misusing and get banned. So they could ban your account, but then you can just create another account. They can ban your credit card. So now it's like, okay, well, you can create another account, but you'll have to associate a different credit card with it. The credit card you used to pay with has been banned, and you're not allowed to use that card anymore. They're identifying you by your credit card, not by your account. Okay, well, you could just get a new credit card or something like that. So there are ways around something like this, or a lot of the games out there now, they have ways where you can buy game time external from it. So you can either pay $15 a month, or maybe you can buy a game token. If you buy them in, you know, 6-month buckets or something, you can get them for $12 a month or something like that. Well, now all of a sudden you're paying for your subscription with a game token, not with a credit card, because you bought the game token with the credit card. So there's ways of circumventing this as well. Okay, well, another thing they could do is they can ban the user's IP address. All right, so now let's assume that this is the computer that, let's say I'm the user and I'm cheating at the game, and they ban my IP address. Well, this guy has a non-routable IP address. So what they're banning here is not my non-routable IP address. They're actually banning the IP address of my home router, the one that has a unique address on the network. If that's the case, then if I'm the cheater, but me and this guy play the same game, then this guy won't be able to play the game either because the router's IP address is banned. So any request coming from this routable IP is now blocked by that game. Now, this person's account would not have been blocked more than likely because chances are it's a both and situation. So they probably ban their user's account and then they also ban the user's IP address. So by my last example, maybe this user, his account is still fine, but he got caught up in the ban because he can't actually play the game because he's sitting behind the same IP address as this other guy that got banned. All right, so what's the problem? So this is where we get to, the computer scientist side of things as opposed to the normal consumer. How do we force our computer to get a new IP address? And actually, in our example here, how do we force our router to get a new IP address? We're operating off this issue of the lease time. All right, so chances are your lease time for your network for the DHCP server on your internet service provider, let's say it's a week, just picking that number out of the sky. So what's one way we can force ourselves to get a new IP address? Anybody have any ideas? If our router got banned, if the IP address of this guy got banned for our video game, and this guy still won, and this guy's account also got banned, so he's screwed. But this guy who's playing the game wants to still be able to play the game, but his IP address is banned. How can he force this guy to get a new IP address? Anybody ever have to do this? No takers? Here, I'm going to just throw a little thing. Given a lease time of a week. So the obvious thing we can do is disconnect the router for a week, then reconnect after the lease has expired, and likely get a new IP. So that's one game we could play, right? We can say, oh, well, if the lease time's a week, I'll just turn off my network. I won't use the internet for a week, turn my router off, wait for the lease to expire, and then I will turn it back on, and it'll ask for an IP address. And because it won't just be handed automatically, handed back the same IP address, presumably I might get a new IP address. All right. Now, how many of you want to be without the internet for a week just so you can get a fresh IP address? Not very many people, right? We're human beings. We're not very patient. All those things. So that's probably not going to fly. What else can we do? Well, let's explain this a little bit farther. I'm going to do it here. Oh, so here, I already said it here. So that lease time is associated with the MAC address of the network hardware. So that means that this router has a unique hardware address. Hardware identifier. It's not an address. It's a hardware identifier, like a social security number you can think of. All right. So it has a lease time with the internet service provider that it's connecting to get to the internet. So this guy, if with his MAC address and a lease time of a week, if he turns himself off for a week and then comes back in, providing the same MAC address, he'll get presumably a new IP address. Okay, so another thing we can do is we can spoof our MAC address. So for any of you who have used a, like one of those Linksys wireless routers or a Netgear wireless router or something like that, you kind of hit your router in your house. You can connect to its configuration through a website. So this guy's actually running a web server. So when you first connect it up, this guy gets an IP address from this, and this guy's address might be like 192.168.1.1, let's say. You can go to that, and that will give you this web interface for configuring your router. And one of the options in there will be to change the MAC address of the router. That is to say, tell this router to pretend to have a different MAC address. So maybe this computer here says, okay, well, I'm going to go ahead and copy my MAC address, and I'm going to tell, well, actually, it'd probably be, since in our example, we're saying this guy wants to get back into his game. This guy's been banned at the IP level as well as the account level. Okay, but this guy, his account's still fine. He just can't join unless he goes over to his friend's house to get onto the network, to get onto the game. But this guy can take his MAC address and type it into the software on his router and tell his router to pretend to have that MAC address. Tell the router to pretend to have a MAC address of one of the internal computers, which will likely force the internet service provider to hand out a new IP address to the router, since that is the first time it has seen that MAC address and a lease is not active. So comparatively here, instead of waiting a week, you can do this instantaneously, and you're only limited by the number of MAC addresses you have available to you, because it still has to be a legal MAC address. Now you can make a guess at the MAC address, since we decided there was how many, the trillion number thing, so all you have to do is guess at a legal MAC address that isn't already leased. Well, actually, it wouldn't even matter for getting by this problem. But if you happen to guess a MAC address for another customer of your internet service provider, you would be handed out the same IP address they have, unless they're currently on, and then it would give you a different one, or probably some sort of conflict saying another computer with the same MAC address already exists. But you can try guessing at a MAC address, but the safer way of doing it is just say, hey, I know that every single computer that's on this network has a unique MAC address in the world. So including this router, I'm just going to tell my router to pretend like he's this guy's MAC address. And if then he gets banned, he can tell him to use this guy's MAC address, this guy's MAC address, this guy's MAC address. And the thing is you only really have to do that for a week. After a week, you can actually switch back, and then this guy would likely get a new IP address since his lease has expired. So you can kind of play the game with that DHCP leasing to now have your home router get a new IP address that is not banned by your video game. And since this guy's account is not banned because he didn't cheat, he is now able to access his game because the router is connecting to it with a different IP address. That makes some sense? So this is kind of some of these kind of fun things you can do as a consumer by knowing, not that I'm suggesting you cheat at games. I'm just saying if you do run into an issue, you can protect yourself to some level by, or let's say that you accidentally had an issue. Let's say you were in this guy's case here, he was banned by association. Somebody else on his network cheated, and now he's paying the price. In that particular case, if he has access to this router, he might be able to fix things. Otherwise he could maybe call the game company and explain the situation, and the game company might be able to somehow release it, or make an exception, whatever it is, presumably because this guy's account is already banned, something like that. All right, but using our knowledge of how MAC addresses work and how DHCP servers work and how NATs work, using our knowledge of all those things, we can manipulate the network to force it to give us a new IP address, if that was handy for us, if that was something that would benefit us. All right, then I'm going to just introduce the next part that we're going to talk about next time. All right, so when we type in www.google.com, what happens? I'm going to add another slide here. That's going to be actually, let's do it this way. All right, so we're going to try to answer those couple of questions next class. All right, the assignment for this week is already up on Blackboard. I know some of you turned in the midterm over the weekend, so I'll get that graded hopefully today. And then I will see everybody on Wednesday morning. I think everybody.
Sure, Dr. Lekha.
I think everybody went to sleep. You wake up just long enough to join the Zoom call. I'll watch the video later. All right. Have a good one today.
You too, sir.
All right. Bye-bye.
Thank you,
You
Dr.
too,
Lippman.
Dr.
Dr. Lippman, this is Syed Moinuddin. Hello.
Hey.
I sent you an email. Can you please help me on that issue? I sent you a separate email, 101.
Did you send it today or over the weekend?
Over the weekend, if you can have an email conversation or a phone conversation, I would.
Yeah, I'll be going through my emails here in a few minutes, so I'll get caught up.
Sure. Thank you, Dr. Lippman.
Okay.
Thank you. Take care. Bye.
Yep.
This is Syed Moinuddin again for your reference.
Yep.
Thank you.
All right. Anybody have anything else before we call it quits? Going once, going twice. All right. See everybody Wednesday.